Hi everyone, this is Mrs. GA, and today we are going to talk about functions. The definition of a function is a relationship where every input has exactly one output. So another way of saying that is for every x, there is only one y. So there were, you probably learned the vertical line test for testing if something is a function. Essentially, if you draw a vertical line at any point on your graph, it should only cross at one point. So that means for every x value, there's only one y value. So something that's not a function would look like this, which fails your vertical line test. And the reason why is for a given x value, there are two y values. So again, for every x, there's only one y. So we're going to start by talking about how to evaluate a function. So essentially, you're just going to substitute the value into your function, replacing this value with x. So here we have f of x equals 2x squared minus x plus 3. And we're going to start by finding f of negative 2. So essentially, you just need to be careful to follow order of operations here. So let's substitute first. I always recommend substituting with parentheses just to avoid small mistakes. So f of negative 2. Remember, order of operations tells us to do exponents and then multiply. So negative 2 squared is positive 4 times 2 is 8. Negative 2 becomes positive 2 plus 3. So f of negative 2 is 13. All right, now let's take a look at the second example where we're finding f of x plus 1. So we're going to start by substituting x plus 1. And we do need to be careful here that we are actually multiplying out our binomial completely and that we are distributing the negative. So this is why I always say substitute with parentheses. So let's start with our binomial squared. So I'm going to show it in multiple steps. X plus 1 squared would be x squared plus 2x plus 1, and I will distribute in the 2 in the next step. Here I'm going to distribute my negative. So I have negative x minus 1 and then plus 3. So let's distribute our 2 to the trinomial. So 2x squared plus 4x plus 2 minus x minus 1 plus 3. And now it's just a matter of combining like terms. So we have 2x squared. Here we have 4x minus 1x giving us 3x. And then here we have 2 plus 3 minus 1, which is 4. So again, general rule of thumb, when you substitute, do it with parentheses. Be careful with something like this. It actually means x plus 1 times x plus 1. Okay, now we're going to be evaluating a piecewise function. So a piecewise function looks something like this. Your function is defined by different subfunctions given different intervals. So I can see for this piecewise function, for all of my x values less than 0, I'm defined by this quadratic function. And for all of my x values greater than or equal to 0, I'm defined by this linear function. So essentially, all you need to decide is when you're evaluating, do I substitute the value into my top row or my bottom row? And that's just going to depend on the x value. So for f of negative 2, since negative 2 is less than 0, I'm going to use my quadratic function to evaluate it. So f of negative 2 is positive 4. For my second one, I'm finding f of 0. So this one you just need to be really careful when you decide which one. So in my top row, 0 is not defined as part of this part of the function. In the bottom row, it says x is greater than or equal to 0. So this is where I will substitute 0. So I get 0 plus 1, so f of 0 is 1. And then for that last part, well, I have f of 3. So that would fall into my linear category. So I'm going to substitute, I do 3 plus 1, which is 4. So it's the same process, it's just you have to do a little bit of extra thinking to decide where do I substitute my value. Okay, so the last thing we're going to talk about is how to find the domain of a function. So the domain is all possible inputs defined for a function, and the inputs, again, are the x values. So you're essentially describing which x values work for your function, or which ones are defined. So really, the ones that at this time we need to be careful about are radical functions and rational functions. So radical functions, we only need to worry about even index, like a square root or a fourth root, because these do have restrictions. The radicand, which is the inside of your radical, must be greater than or equal to 0. So this will create a domain restriction. So essentially, just remember that we're going to be setting our radicand greater than or equal to 0, because you can't take the square root of a negative number. The other one we need to watch out for at this point are rational functions. So those are functions that look like fractions. The reason why we need to look out for these is because we know that the denominator cannot equal 0, and we know that creates a domain restriction. So we are going to be essentially setting our denominator equal to 0 to find our restrictions. Okay, so here we're going to state the domains of the following functions. We'll do this in set builder and interval notation. So if you just have a regular polynomial function like this, our domain is always going to be all real numbers. So we can say x such that x is all real numbers, so that's our symbol for all real numbers. And for interval notation, all real numbers would be negative infinity to positive infinity. Okay, so let's look at this second one. So remember, if you have a rational expression like this, we do need to watch out for our domain restriction. So first I'm going to start by factoring my function. So I have x minus 6 times x plus 3. So remember, our denominator cannot equal 0. So that means that we have two restrictions. We have a restriction when x is 6 and a restriction when x is negative 3, because those would create a 0 in our denominator. So in set builders, we can say x such that x is not equal to 6 or negative 3. And that is fine. And so all other numbers would work. So for interval notation, it's a little bit more convoluted. We have to say from negative infinity to negative 3, from negative 3 to 6, and then from 6 to positive infinity. So that's kind of a roundabout way of including all numbers except for negative 3 and 6. Okay, so for our next example, I see that I have a square root. So I know that it is not possible to take the square root of a negative number. So that means I need to take my radicand, which is everything inside, and I need to say that this must be greater than or equal to 0. And notice that 0 is included because it's okay to take the square root of 0. So now I'm just going to solve this inequality. So I'm going to say 0 is greater than or equal to x squared minus 9. So I added x squared and subtracted 9, and now I'm going to solve the inequality. So I'll factor it out to find my critical points. And I am going to test my zones. So I see that my critical points are at 3 and negative 3, and both would be included. I'm going to go like this. And let's say I test x equals negative 4. That would give me a negative times a negative, which is a positive. Let's test x equals 0. That would give me a positive times a negative, which yields a negative. And let's also test x equals positive 4. So we have a positive times a positive, which is a positive. So for this one, I'm looking for whenever my function, whenever this quadratic equation is less than or equal to 0. So I'm looking for this region in between. if it helps, you could flip the order of this. So x plus 3, x minus 3 is less than or equal to 0 to help you interpret that we want the negative values. So that means that our domain is everything between and including -3 and +3. So we can say in set builder notation x such that, and we'll use intervals, or we'll use inequalities here. So everything from -3 to +3, including. Or if we want to do interval notation, it would be bracket -3 to +3 bracket. Okay, so for this last example, we actually have two things here we need to watch out for. We have a rational function, so we know that our denominator cannot equal 0, but we also have a radical expression within it, so we know that our radicand must be greater than or equal to 0. So typically I would say look inside your radical, and I would say to do this, say t plus 1 must be greater than or equal to 0. However, in this case, since our radical is in the denominator, it cannot equal 0. So in this case, I'm actually just going to say t plus 1 is greater than 0. And if I solve that inequality, I get t is greater than -1. So in set builder notation, we would say t such that t is greater than -1. Or in interval notation, we would say -1 to +infinity. Okay, that is all for today's lesson. Thank you so much for watching.